Elastic rebound theory and the omega sequences. Introduction. In the classical seismology, the elastic rebound theory is an explanation of how energy is accumulated, and then released from the rock during an earthquake. The model was formulated by Reed in 1910. Due to the slow and constant movements of the tectonic plates, the rocks on the opposing sides of faults are subjected to the shear stress. They deform slowly, until their internal rigidity is exceeded. When the actual earthquake nucleates, the rock is split with a rupture along the fault, partially releasing the accumulated energy. The rocks around the fault snap back toward their original shape. Problem. The problem with the Reed rebound model is that it is based on a single fault, excluding any possible interactions among them. The advantage of the omega theory is that it expands and upgrades the Reed rebound model, with the incorporation of a minimum of 2 and usually multiple faults. This extended model also accounts for potential interactions among faults and block rotations between the fault planes. In structural geology, such rotations are well known to occur within the systems of interacting subparallel faults, where they are referred to as the domino-type rotations. Solution. To obtain a solution, we need to analyze how the elastic rebound model is applied to a system of 2 interacting parallel faults. In their initial state, the rocks are undeformed. Due to the increase of shear stress, the rocks are elastically sheared and rotated. After the internal rigidity of the rock is exceeded, the earthquake occurs, first as the main shock along one fault, followed by the aftershock along the second fault. During this process, the block of rock between both fault planes rotates back toward the original position. Careful mathematical examination of this process within the omega theory shows that the parallel faults interaction can happen between equal and also non-equal sized parallel faults. Let L1 be the length of the first fault, while L2 is the length of the second fault. The omega theory shows that the ratio B between L1 and L2 is a parameter of the rock itself and depends on the frictional properties of the rocks and their geological settings. The theory also shows that the reactivation time is linearly proportional to the length of the fault. This means that larger faults will need more time to reactivate and produce an earthquake compared to smaller faults. In nature, there is a considerably large number of small earthquakes in comparison to larger earthquakes. In the case of several interacting subparallel faults, this leads to the development of either periodic or geometric series of interacting faults. When the fault series is periodic, all interacting faults have the same lengths and the distance between them is also equal. When the fault series is geometric, the length of each subsequent fault is b times larger, compared to the previous one. Also, the distance to each subsequent fault is b times longer compared to the previous one. The existence of such periodic and geometric series of faults is most evident at the mid-ocean ridges. These have segmented structure, composed of long subparallel transform faults and fracture zones separated by ridge segments, where the Earth's crust is pulled apart. Careful measurements of these structures clearly show that the series of both the transform faults as well as ridge segments tend to be geometric. Analysis of the seismic activity of such series of faults shows that they produce cascades of earthquakes, which are also periodic or geometric. This is well in accordance with the omega theory. Such cascades of earthquakes are generally referred to as the repeating earthquake series, and in the omega theory they are called the omega sequences. Within the omega sequences, the seismic activity is systematically transferred from one fault to all subsequent parallel faults. The easiest and the most effective way of illustrating how the omega sequences work is an example of the falling dominoes. If all dominoes are of equal size, the sequence of events is periodic. But if the dominoes form a geometric series, the sequence of events is also geometric. Thousands of such periodic and geometric omega sequences are constantly occurring in the Earth's crust in all seismic zones along tectonic plate boundaries. Types of the omega sequences. There are 4 basic types of the omega sequences. Decreasing seismicity rate sequences are characterized by the systematic transfer of the seismic activity, from smaller to larger faults. Increasing seismicity rate sequences are just the opposite. Here, the seismic activity is systematically transferred from larger to smaller faults. Decreasing to increasing seismicity rate sequences are those decreasing seismicity rate sequences that transform into the increasing seismicity rate sequences. Increasing to decreasing seismicity rate sequences are those increasing seismicity rate sequences that transform into the decreasing seismicity rate sequences. Can omega sequences be found in nature? Careful mathematical analysis of the seismic activity of the Earth, as well as earthquake series worldwide, shows that the omega sequences can occur everywhere, not just at the mid-ocean ridges. Seismic catalogs were long thought to be composed of random events. Yet, the omega theory showed that these supposedly random catalogs are actually composed of a multiplicity of the omega sequences, which represent a concealed order within the seismic activity of the Earth, and as such being far from random processes.